All right, so this will be the 10th lecture in operations research. So the third point on the board is Happy New York Yankees Elimination Day. So why is this a topic for the course? Other than, of course, as a Red Sox fan, it's wonderful to have an opportunity, even though the Sox were just swept by the New York Yankees, so we'll give credit where credit is due. Anybody know how elimination numbers are calculated in baseball? Yes? I'm sorry? That's a good way of doing it. That's not how Major League Baseball does it. Major League Baseball and ESPN often look at where two teams are, and they say, how many games does one team have to win, the team above, plus the team above it have to lose, to guarantee that the team below can't leapfrog the team above. What this doesn't do is take into account the fact that there could be teams above you that are playing each other, so it's not possible for certain teams to all win. In 2004, probably the greatest year in the history of mankind, the Red Sox clinched the wild card one day earlier than Major League Baseball predicted or thought, because there was still a chance that the Angels could catch the Red Sox for the wild card, and there was a chance that the A's could catch the Red Sox for the wild card. But one of the Angels or A's had to win the American League West, and they had a 3-game series. So one of those teams had to get 2 losses. And so the calculations that MLB was doing was just saying, well, what if this team wins all their games? What if this team wins all their games? And they were taking into account head-to-head matches. There's some really good work about calculating elimination numbers correctly by using linear programming. And what you do is you calculate all the teams at once. So it's a really interesting problem as to how to do the calculation efficiently. You can do it, team by team, but it's nice to do it all at once. Right. There's also going to be a lunch today at noon at Mission. If you don't have a meal pass, I will swipe you in. We have a guest who's a Williams alum who has been involved in the medical industry for many, many years. If you are doing the health project, it would be really good, apologies for the short notice, to come to that and just talk to somebody who is quite aware of a lot of the issues. And then there will be a faculty colloquium at 1 p.m. And then the Major League Baseball meeting is at 2. Okay, so the loud voices won and decided to have us do the proof that if there's a basic optimal, if there's an optimal solution, then there's a basic optimal solution. So it's not a bad idea to do this. It will review the main ideas in the proof that feasible implies basic feasible with a small twist. What do you think the biggest twist is going to be? The biggest difference between proving that optimal implies basic optimal versus feasible implies basic feasible? What do you think we're going to have to use now that we did not have to use before? What should come into play? Yes? Yeah, the cost function, right? That should have some role in what we're doing. If we're trying to prove something about the optimal function, this is where you would expect the objective function to come in. When you're just trying to prove the existence of a feasible solution, the objective function is not important.
So, basically statement, given an optimal solution, there's a basic optimal solution?
Yes.
That does not mean that the basic optimal solution has lower cost. That just means that
No, it does.
That just means there's an optimal solution that that is only present in the basics, right?
It doesn't mean, it means it has a cost as low.
Really?
Yes.
Okay.
Because otherwise it wouldn't be optimal. Optimal is smallest cost. So it doesn't say that if you look at all the solutions, the basic optimal is cheaper than any other alternative, than a non-basic alternative. It just means if you have a optimal solution that's not basic, there's an equivalent one. There's one that has the same cost but is basic. And the whole point of this is to allow ourselves to restrict the space we look at. And again, you may not care that your solution is basic optimal. But if all you care about is the final objective function, then you don't really care how many components are 0 or not 0. All that matters to you is the final cost, and you are indifferent between all solutions of the same cost. And since you're indifferent, why not choose a path that lets you get to an optimal solution easily? That's the whole point of all this. Later on, we will start adding in additional constraints. We will start being picky. And then in those situations, we will then have multiple things to deal with. But right now, all we care about is the final cost. We don't care how we reach that. Okay? So the theorem is, consider a canonical linear programming problem if there exists an optimal solution, then there exists a basic optimal. Okay, so the proof is going to be by contradiction, and it's going to be by method of descent. So exactly as before, we might as well assume that there's a optimal solution, otherwise there's nothing to do, and we'll assume it's not basic. So proof. So assume there exists an optimal that's not basic. And in fact, none are basic. So I can even be a little bit stronger, and we'll say none are basic. Because if there was an optimal solution that was basic, we'd be done. So let's assume all the solutions that are optimal are not basic. So what do we have? We have AX equals B. We have X, I guess it's C transpose X, is minimal. X is greater than or equal to 0. So these are our constraints over here. That's the objective function. And the entries, the columns of A corresponding to the non-zero entries of X, what do we know about them? So what do we know about the corresponding columns? Yes? Linearly? No. Almost. Linearly dependent, yes, off by a minus sign. There. So why are they linearly dependent? Because it's not basic, right? If it was basic, they would be linearly dependent. We're trying to prove, in fact, that they are linearly independent. So what does that mean? Well, we can do the same without loss of generality that we did last time. Why not just shuffle the non-zero entries and assume the non-zero entries are the first k? So without loss of generality, x1, x2, ... xk are greater than 0. The rest are 0. Otherwise, we have to have subscripts, I sub 1, I sub 2, I sub 3, I sub 4. So we'll just assume that we are in the situation like this. Okay, so since linearly dependent, there exists alpha 1, alpha k, such that alpha 1, a1 plus alpha k, ak is the 0 vector. That's what it means to be linearly dependent. And not all alphas are 0. So in particular, if not all the alphas are 0, what do we know? What can we assume without loss of generality? Yes?
The first one.
Yeah, without loss of generality, the first one is non-zero. And without loss of generality, alpha 1 does not equal 0. Because when we have a linear dependence, we're not going to, of course, consider 0a1 plus 0a2. Linear dependence means the sum combination where they're not all 0. We'll also assume that we don't have a column that's all zeros, because if we have a column that's all zeros, that variable has nothing to do with the problem. Okay, so we have this wonderful relation, and we also know that we have a optimal solution. It has minimal cost, and it solves this equation ax equals b. So what this means is we can construct new solutions. So let's consider x sub t will be x minus t alpha 1, alpha 2, alpha k, and then all zeros. And I have the following claims. The first claim is that the coefficients are greater than or equal to 0 if the absolute value of t is small. Well, to see this, what's the simplest value of t to check? Simplest value of t to check. 0. So if we take t equals 0, this all vanishes, and we get it's just the vector x. And since x is optimal, x must be feasible. If x is feasible, it has non-zero entries. I'm sorry, non-negative entries. And so some of its entries will be positive, some of its entries will be 0. If t is sufficiently small, well, these zeros at the end, they always stay 0. It doesn't matter what t is. And for the stuff in the beginning, if t is sufficiently small, all of these correspond to non-zero entries over here. So I'm either subtracting or adding a little bit from the non-zero entries x. If I take t sufficiently small, it's still going to be positive. And what you can probably do is maybe take t to be less than or equal to the minimum over all I such that alpha I does not equal 0 of xi divided by alpha I. Probably something like that would work. Okay? And so as long as I don't move too far, this vector is going to have non-negative entries. The next claim is axt equals b. And the reason is we know ax equals b. And if we apply a to this vector, what do we get? 0. That's the whole point of the linear dependence. And this is from ax equals b and alpha 1 a1 plus alpha k ak equals 0. Therefore, what do we know about this vector xt? So what must be true about xt? It's a solution. So xt is a feasible solution. And so what we're doing is we're going from one solution to a whole family of solutions. And the idea is if we choose t appropriately, we should be able to get a contradiction. So what do you think we need to look at now? Where are we going to get a contradiction? Yes?
I mean, we can recursively apply the xt relation until we get a basic solution. Right? I mean, say, consider that this new xt is still non-basic.
Okay.
Then we can say that we can do another relation for alpha 1 to alpha k, or alpha 1 by alpha k minus 1, etc., until we get a basic solution that is feasible. Right?
All right, so
That's the proof we did last class.
that's the proof we did last class, but we're not. What piece of information must we use somewhere? We're not using optimality.
Right.
So suggestion.
Yeah, I think it would be easier if we know that there's at least one value in xt that's less than the value of x that we had in the beginning. If you apply the cost function to it, the cost should be less.
So we want to somehow get to a lower cost.
We have a lower cost right now, right? If you just do c transpose times xt, you should get a lower cost because every value in c transpose is positive.
I think we should get equal costs, right?
Okay, so there are some issues here. Somehow we definitely want to use the cost function. It is possible the cost does not change. And we'll see in a moment that it's possible that the cost does not change. Now there is one thing I've mentioned but I haven't written down that I want to assume about this vector x. Everything we've done up to now is correct for any optimal solution. I want to impose an additional assumption on this optimal solution. What should I assume? How did we get a contradiction last time? What were we able to do? Yes?
We made t great enough so that one of the x's was 0.
Okay, so we made t great enough so that one of the coordinates became 0. In fact, it might be that 2 or 3 become 0 at the same time. But there's going to be a critical threshold of t, the smallest in absolute value, where at least one coordinate becomes 0. Excellent. Why is that bad? Why is that a contradiction? Yes?
The first solution we worked with, we assumed
So we didn't write that over here. This was the method of descent. We assume we have a solution with a certain property, and we assume that it's the minimal of all of those. And then we find something that's even smaller. And so what we want to do is we're going to assume that, and we will assume fewest non-zero entries. And this is where we're using the method of descent. This is the big item over here. And again, this is the difference between being at the Ohio State University and a university in Ohio. I am not asserting that there is one optimal solution that has the fewest number of entries. There could be a whole class of them. I'm saying consider all the optimal solutions and order them by the number of non-zero entries. Look at all the ones that have just one non-zero entry, two non-zero entries, three non-zero entries. Because the integers are distinct, and because the integer we're looking at the number of entries, can't have a negative number of entries. It's got a lower bound. So there will be, as soon as there's an optimal solution, there will be at least one with the fewest non-zero entries. There may be more than one, but all we need is the existence of one. So now we assume that we have an optimal solution with the fewest non-zero entries, and we've just constructed a new solution. Let's look at the cost. So what is the cost of x of t? Well, the cost is just C transpose xt, which is going to be C transpose x minus t, and it'll be C1 alpha 1 plus CK alpha k. And notice this part here is fixed. Right? So this tells us how much the cost changes by when we pass from x to x of t. What's the simplest value of t to study? 0. And good. When we take t equals 0, it just reduces to the old cost. So what kind of cases do you think we're going to break this up into? So I want you to get a sense of how you would attack something like this. What should our cases be? You know, when you're looking at this, what do you think the key factor is?
It's positive.
Yeah, if it's positive, negative, or 0. There's 3 possibilities. Right? Universe likes 2 and 3 for many things. You know, yes or no, on, off, true, false, that's the binary. The comparisons, with the real numbers, greater than, equal to, or less than. So there's 3 cases. So case 1, the C1 alpha 1 plus CK alpha k is greater than 0. Well, if this is greater than 0, what should we do? Which direction should we move? Yeah, choose a small positive t, cost is lower. Cost is lessened by small positive t. And that's a contradiction. It contradicts the fact that we had an optimal solution. We just found a way to lower the cost. You can't lower the cost. All right, what about case 2? Well, in case 2, what do you think the next easiest case to analyze would be? Do you think that's the easiest one, or do you think that's the next logical one? I think less than 0 is easier to analyze because it's essentially the same as this. Equals 0 is a little bit different. I mean, it doesn't really matter, but I think this is very, very similar to this. What should we do in this case? Well, question?
Yeah, so that would imply that the t was negative, which would mean that you have to add x to get an x to 0.
Are we talking about case 2?
Yeah.
Yeah.
But wouldn't that imply that there was an x that was less than 0, which was not in our assumption?
No, because remember the coefficients of x, the first k coefficients are all positive. If t is sufficiently small, then we're still going to have a positive vector. Think of t as 1 over 10 to the Google. And it's going to be such a small blip, it's not going to really change things. So similarly, cost is lessened by small negative t contradiction. So if this quantity is not 0, we have a contradiction. So there's only one possibility left, it's 0. So case 3, C1 alpha 1 plus CK alpha k equals 0. And in this case, what it's saying is no matter what xt you have, they all have the same cost. So all xt have the same cost. Therefore, what do you know about xt? Xt is optimal. So that's the nice thing. The only case that's left has each xt being optimal as well. We didn't know initially that xt was optimal. We just knew that it was still feasible, but maybe we screwed up the cost. Now we've just shown we haven't screwed up the cost. So now what we do is we do exactly what we did before. We increase t either in the positive or the negative direction until we come to a place where at least one coordinate vanishes. And now we'll have an optimal solution with fewer non-zero entries, contradiction. So now increase t, or maybe increase absolute value of t until at least one entry vanishes. Therefore, you have an optimal with fewer non-zero entries. And that's a contradiction. And that finishes the proof. Okay. It's very similar to what we did before. The real twist is that now we have to put in the objective function and see how that's going. But the nice part is 2 cases are immediately handled, and then the third case, it's the same argument as before. We keep slowly increasing t in either the positive or the negative direction until at least one coordinate becomes 0. And now we have a solution with fewer non-zero entries. That contradicts our assumption. Therefore, there must be a basic optimal solution if there's an optimal solution. Okay? If this was a theoretical class, this would be time to celebrate. There's now only finitely many things to check, and we only have to check things of a given form. Right? This is wonderful. So what's the question you want to ask? How big is finite? And so we gave some upper bounds as to how big finite could be. It would be, I think, of size like 2 to the n. It can be quite bad. N could be of the size, 10,000, 100,000. So I was actually showing Cam and Kayla this morning fast multiplication and showing them how to get these things down to a reasonable size. They're not having too much fun in their math classes. But imagine instead of having something of size 10 to the 200, which I can handle, what if I give you 10 to the 200 to the 10 to the 200? Even fast multiplication is now worthless for us in terms of being able to handle that. That brings me down to I have to do something on the order of 10 to the 200 operations. Even with fast multiplication, I can't do that. Okay? We need to make sure that not only is the set of basic feasible and basic optimal solutions finite, but it's a finite that's accessible. So what I want to do is I want to do a little bit of a detour and talk to you about some nice problems in mathematics where there are finitely many solutions, but the finitely many is not always that accessible. And the reason I'm doing this is for first course, it's too much to go into a true analysis of how fast the simplex method runs. It runs quickly most of the time, but it's beyond the scope of this course to prove that. Now, when you try to use it, it runs fairly quickly. So what I want to do is I want to just show you a couple of old algorithms. One of them you've almost surely seen. It's the oldest, I think, non-copyrighted proof in mathematics that's still being used. Anybody have any idea? It's a number theory result, going back to Euclid. There exists infinitely many primes. Okay. I will use the more modern language to describe this than what Euclid did. If anybody wants to see the original language, let me know. In some years, I actually lead trips to the Rare Books Library, and we actually have a first edition of Newton's Principia. And if you want to see what calculus used to look like, it's interesting to see the very geometric language they used to describe things like calculus. So proof by contradiction. Assume not. So P1, P2, ... Pn are all the primes. And then consider xn equals P1 times P2 times Pn plus 1. And we know the first prime is 2, the second prime is 3, so there's at least a couple of primes. Can this number be prime? Yeah. Can the number be composite? Also yes. It's greater than 1. It's either prime or composite. Can P1 divide this number? No. Neither can P2, neither can P3. So this is not divisible by P1, P2, Pn. Therefore, it's prime or divisible by a prime not on our list. Therefore, there exists infinitely many primes. Okay. This is one of the oldest proofs that still is taught. What we can do is we frequently let pi of x denote the number of primes. So pi of x is the number of primes less than or equal to x. The prime number theorem says this is approximately x over log x. If you want to do a better job is you integrate from 2 to x of dt over log t. That does a little bit better. What this means is that there's a lot of primes. How many perfect squares are there up to x, approximately? Root x. How many even numbers are there up to x, approximately? X over 2. So what this is telling you is there's not as many primes as evens. In the limit, 50% of all numbers are even. X halves divided by x is 1/2. 0% of numbers are prime in the limit. The density of primes up to x is about 1 over log x. So the density is going to 0, but slowly. It's going to 0 like 1 over log. Whereas if you consider perfect squares, the number of perfect squares up to x is about root x. The density would be 1 over root x, which is going to 0 very fast. So there's a lot more primes than perfect squares. If you use Euclid, you get this result that the number of primes is greater than or equal to some constant times log of x. It's a really bad result. Okay. If people are interested, I have some fun reading on stuff you can do along these lines.
Log x like basically 4 for any practical purpose.
For the numbers we'll be looking at, yeah. Well, it also depends a little bit on what base you're using, but it doesn't matter. Log x really does not change for the numbers we look at. It's extremely small. So this is a horrible, horrible growth rate. Okay? So what I want to do is I want to write down a couple of numbers now. What's the first prime? 2. Let's apply Euclid's method. 2 plus 1 is 3. What's the smallest prime that divides 3? 3. All right, let's apply Euclid's method again. 2 times 3 plus 1 is? Smallest prime that divides 7. Let's apply Euclid again. 2 times 3 times 7 plus 1 is? 43. What would you conjecture? What do you conjecture for Euclid's method?
Probably prime.
I'm sorry?
Every next number you get.
Yeah, doesn't it seem like they're all prime? If you continue the calculation, the next one is 13. I'm doing the smallest number that divides what happens when I apply Euclid. So if I do 2 times 3 times 7 times 43 plus 1, what's the smallest number that what's the smallest prime that divides that? It's 13. So unfortunately, the conjecture that it's prime fails. Next one is 5. The next one is 6, 2, 2, 1, 6, 7, 1. I'll post these. You don't have to write them down. Then 3, 8, 7, 0, 9. If I really loved you, I'd memorize this. 1, 8, 3, 8, 1, 0, 5, 7, 1. 139. 2, 8, 0, 1, 11, 17, 5, 4, 7, 1. And this is called the Euclid-Mullin sequence. Okay?
Those guys seem like contemporaries.
They seem like what?
Euclid and Mullen, like they're very close.
Do you know what anticipatory plagiarism is? Anticipatory plagiarism is when Gauss steals your great idea 200 years before you were born. So you can do some things like that to get some of these people involved in the game. All right? This is a strange sequence. There's a lot of questions you could ask. What's a question you might want to ask about this sequence? I'm sorry? Yeah, does it hit every prime? This is an extremely difficult sequence to work with because we have to factorize larger and larger numbers. And so the number of terms we can compute, I think, is on the order of somewhere between 20 and 60, maybe around 40. We do not know many terms of this sequence. Just because we have a method to compute something does not mean we have a good method. And I really want to just drive home this point because we're not going to prove in full detail why the simplex method works as well as it does. Just because we've cleaned something up a little bit does not mean we've made it practical. How many of you have ever seen the Euclid-Mullin sequence? How many of you have seen Euclid's proof of the infinitude of primes? Yeah, this is something that you could have seen years ago. Just you've got this method, it generates infinitely many primes. And no one thought to see what happens when you try to use it? What kind of sequence of numbers does it generate? How quickly is it generating primes? What's the density? The numbers are coming in all over the place. Right? We're going backwards and forwards. What's going on? So I really want to just use this as a cheap way of driving home a nice point. The last is, if anybody's looking for colloquium, one of the great colloquiums or standard colloquiums is, there's lots of proofs of the infinitude of primes. One of my favorite quotes by Paul Erdős is, you do not need to believe in God to be a mathematician, but you do need to believe in the book. So the book is where God keeps all the best proofs of results. And some entries have multiple proofs because there's just lots of really good, elegant ways. And a couple of mathematicians actually collected what we think is a human approximation to this book. And chapter 1 is 6 proofs of the infinitude of primes. So this is one of them. Another one is Fermat numbers. So Fn is 2 to the 2 to the n plus 1. Okay. What's F0? Three. So I'm trying to think did I make a mistake in here? Or do I want to start with a minus 1? No, this I want to do the side. F1. F2. Anybody notice anything about these numbers? They're all prime. F3. 257? Is 257 prime? Seems reasonable. Is it a multiple of 3? No, the sum of the digits is not 3. Is it a multiple of 5? No, clearly not even. If you want to check 11, 2 plus 7 is 9, minus 5 is 4. It's not a multiple of 11. So you can check. The next one is also prime. And it's conjectured that that's it. That after that, no more numbers of this form are prime. If people want eventually, I'm happy to give you a heuristic as to why only 3 choices of n lead to a prime. I know there's 5. The heuristic has some issues. But there's only finitely many. That's a big conjecture. You can use this to prove infinitely many primes. And I won't go through the details. I'll just leave it as a post. You can prove that any 2 Fermat numbers are relatively prime. So the greatest common divisor of Fn and Fm is 1, unless you're stupid and take n to be m. So if the Fermat numbers are relatively prime, every time you take a new Fermat number, that's going to give you a new prime. This is going to be a horrible rate of growth. Your numbers are growing exponential. Okay? So the point of all this is that we have many methods in mathematics that work, that are nice, that are easy to implement, but are not practical. If you want to use this to generate primes, these numbers are growing extremely rapidly. And we would have to factorize these huge numbers. So the question is, are there better ways to attack? This is not a number theory class, so I will stop it here. But I just wanted to do this as a little bit of a warning as to what's going on. OK. It's now time to go to the simplex method. So what's nice is a lot of people have spent a lot of time programming and coding things such as the simplex method and twists on it. So a lot of systems have the simplex method already programmed, or even better versions of it. So what I want to do is I want to talk a little bit about the simplex method. We're going to modify the canonical linear programming problem just a little bit. We've already seen the advantage of having a problem in a certain form. And the advantage of having it in this form is that when we were doing our arguments, we could assume we had certain structures. And it allowed us to really keep under control the number of cases we have to consider. So let's go to the simplex method. The proof of the simplex method that we'll see is, I think, one of my 2 favorite ideas in mathematics. At first, it seems like something absolutely absurd that you should go to mathematical jail for doing, but it turns out it works. All right? So we have the canonical linear programming problem. Canonical linear programming. So we have ax equals b. We have x is greater than or equal to 0. And we want to minimize c transpose x. And these are the constraints, and that's the objective function. Okay. We're going to make a couple of additional assumptions. Assume the following. 1, A is a m by n matrix with m less than n. Okay. Does that seem like a good assumption? Yes. Why not? Well, I mean, OK, I'm writing it on the board, so it's probably a good assumption. Why is this a good assumption?
It's true unless A is a square matrix.
OK, so if A is a square matrix, then m equals n. And if A is a square matrix, what do we know about solving AX equals B? It's probably trivial. It might depend a little bit on whether or not there's a null space. But if A is an invertible matrix and it's square, there'll be one solution. We're not going to really have that much to work over. If there is a null space, then maybe we can reduce the size of A. The whole point is we don't want to have an overdetermined system. If we have an overdetermined system, we'd be lucky to get even one solution. And so this is to force us to be undetermined. The easy way to phrase this is, if you want to search through a set to find an optimal element, it's nice to have more than one element in the set. It's also nice to have an element in the set. And so if we don't have something like this, we don't really have the opportunity of gaining any efficiencies. All right, the next one is the rows of A are linearly independent. What do you feel about this one? What would happen if the rows of A are not linearly independent? Yes?
You could just remove one of them.
Not necessarily. You may not be able to just remove one of the rows of A. Why might you not be able to remove one of the rows of A? I'm sorry? Yeah, so either you can remove one of the rows of A if the corresponding entries of B are the same, or if they're different, then you have an incompatible system of equations. I want this to equal 5, and I also want it to equal 7 at the same time. We all agree that this is also a reasonable constraint. All right, the next one is B is not a linear combination of fewer than m rows of A. That one's longer than the others. Does that seem reasonable? We'll put that one on hold for a second. And the last one is I want B to be greater than or equal to 0. We chose x to be greater than or equal to 0. Now I want B to be greater than or equal to 0. Do you think it's a big constraint to have B greater than or equal to 0? What would I do if one of the entries of B was negative 5? So what would I do if an entry of B is negative 5? Yes?
Maximize the corresponding, B.
Yeah. I want my entries of B to be greater than or equal to 0. If one of the entries of B is negative 5, I can't just change the constraint. I can't just make B 5. What could I do? So where does B surface? It surfaces in AX equals B. If let's say B1 is negative 5, what should I do to the matrix A? I want B to be positive. I want to replace the negative 5 with a 5. Do you mind if I just go into your bank account and change your positive balance to a negative balance? Does that bother anyone? Okay, you can't typically just go in and multiply by negative 1. You have to do the same thing to both sides. So if I change the first row of A by multiplying all the entries of A by negative 1, then that's the same as changing the sign of B in that entry. So I cannot simultaneously adjust A and B, but I can adjust one of them. If needed, multiply a row by negative 1. So the last one is that B is not a linear combination of fewer than m rows of A. All right? Well, with high probability, my matrix A, we have m rows, and these are vectors in n-dimensional space. So the rows of A live in Rn. Right? And we know that m is less than n. So what do you expect the dimension of the row space of A to be? Again, I can always come up with a strange matrix, but what would you expect the dimension of the row space of A to be? If I choose my rows, say, randomly, with high probability, what should the dimension of the row space be? M. The dimension is going to be at most m. It's going to be at most n. Since m is smaller than n, it will be at most m. It's very unlikely that I would choose and have some kind of linear dependence. So if I choose two directions in the plane, what's the probability that I chose two directions that are linearly dependent? It's essentially 0. If I choose three vectors in R3, and it may not be quite clear that this is 3 dimensions, but if I choose three vectors in R3, with high probability, they're not all going to be in a common plane. And so if I choose three vectors in R3 with high probability, it will be a three-dimensional space. So it is extremely likely that A should have dimension m. Also, given assumption 2, where we assume that the rows of A are linearly independent, we can cross from we expect to it is. Right? So we don't even have to worry about this. We're now assuming we don't have some kind of generic, we don't have a degenerate matrix, we have a generic matrix. What would it mean for B to be a linear combination of fewer than m rows of A? It means it would be living in a very special subspace of the row space of A. What's the probability that you're in one of these subspaces? So for instance, imagine A just has 2 rows, and these are the 2 rows. If I tell you I want to make sure that B is not a linear combination of fewer than m rows of A, that means B cannot lie along this line, and B cannot lie along this line. What's the area of that in the plane? The area of that is 0. If I now had a 3-dimensional space, if I had A having 3 rows, and I say I want to make sure B is not a linear combination of 2, then that means B does not lie in the xy plane, it does not lie in the xz plane, and it does not lie in the yz plane. The area or the volume of those 3 planes in 3-dimensional space would be 0. So essentially, if you're choosing your entry, your vector B randomly, the probability that it lands in one of these lower dimensional spaces is 0. If you happen to land in one of those lower dimensional spaces, however, assumption 3 is violated. So what you do is you tweak B by a small amount. Tweak some of the entries by like 10 to the negative quadrillion. That's not going to really change these constraints that much. I now require that I have to have just a little bit more iron each day. And so most of the time, we can do a little tweak like this and not worry about B being a linear combination of fewer than m entries. OK. But I would say 3 is the most involved of all of them. OK. Any questions on what we've done so far? We have just enough time for the miracle. All right. So Simplex method. Was there a question or? OK. So phase 1, it is find a feasible solution. And actually, I think it's going to be a basic feasible solution. Or prove none exist. And then phase 2 is given a feasible, we find an optimal, or prove none exists by constructing a sequence of feasible with the cost going to negative infinity. Right? So there's 2 steps to the simplex method. You find a feasible solution or you prove that none exist. And then, once you have a feasible solution, you find an optimal solution, or you show that there's no optimal solution by giving yourself a chain of solutions where the cost is going to negative infinity. All right, and the way it works is the following. So proof. Assume can do phase 2. Show can do phase 1. using phase 1, show can do phase 2. And that's the outline of the proof. What looks strange about this? So we assume we can do phase 2, and we use that to show that we can do phase 1. And then, using phase 1, we show we can do phase 2.
Circular.
Yeah. So actually, I should replace the QED symbol, which is a square, with like a circular QED symbol. It seems like this is a bullshit argument. That's a technical term. I'll have to edit the tape later. It is not illegal. There is a way to do this and not be circular. And so we will see that on Monday.